To answer the question, what is ZIO, I'm going to take you on a quick tour, and I'm going to do this fast, so fasten your seatbelt. ZIO is a Scala library for functional programming. It was created by John DeGoes. He's a founder of ZIO, a company that sponsors my free videos. ZIO has lots of other contributors, and you can see that from the GitHub page right here, where it's been forked over 1,300 times, has over 4,000 stars. Then if you look down here, you see 648 contributors. Not only is ZIO popular, but it has all these sub-projects, and you can see the numbers on all of those. So we say that ZIO has a robust ecosystem. ZIO also powers some of the biggest applications in the world, and you can see some of the most well-known names here. Now, I mentioned that ZIO is a Scala library for functional programming, so an excellent question next is, what is functional programming? One way to explain this is, if you know Java, you know how we create a mutable variable like this, and then sometime later in life we mutate that value right there, we change it to something else. In functional programming, you don't do that. We say that mutation is bad. It's bad in the single-threaded world, and as you can see in this quote from Martin Odersky, it's absolutely horrible in the parallel world. So what you do instead in functional programming is, if you're using Java, you would make all variables final. And that way they can't be mutated. If you try to mutate it sometime later, that will be a compiler error. And if you think about this, you know what this is like? This is like algebra, where variables can't be mutated. So when I say variable, I mean algebraic variable. And to this point, when you define variables with the val keyword like this in Scala, they are final by default. So if you try to change it later, this code won't even compile. So that's one example, and now if we get back to Java, you know how you create a mutable list where you can add elements to it and then remove elements from it? Well, guess what? We don't do that either. Instead, what we do is we use an immutable list. This is a list class in Scala. It's a singly linked list, which is immutable. And we use an immutable or final or algebraic variable with it also. So I start by populating this list with 1,000,000 elements. And then in functional programming, or ZIO to be specific, what I can do is I can create a new list from that original list using code like this. And what this does is it goes through all 1,000,000 elements, multiplies each value by 10 to create that new list. And a cool thing about this is that it does this in parallel. So the for each par method lets us do all this in parallel, as I note right there. But one thing about this is you can actually have too much parallelism. And another cool thing that ZIO does for you is it lets you control the number of fibers. So if you know that you have 16 cores on a computer, it's actually very smart to say, you know what, I want to limit the parallelism to 16 fibers at one time. And if you think about that code, that's a little mind-blowing, right? Because if you look at this code right here, you can see that what we did is we create a new list, we multiply 1,000,000 elements by 10, we do that in parallel, we limit the number of fibers, and we do all of that in just about 3 lines of code right here. And notice that we did that with no mutable variables, no mutable data structures, and no impure functions. And this brings up a really good point. What is a pure function? And in one of my books, I have this long definition of a pure function, but basically the input parameters only come in through the front door. The pure function does not modify those parameters. It does not modify any other hidden variables or anything in a global state. It does not communicate with the outside world. When you call a pure function with the same input, you always get the same output. It returns output for all possible values, and it does not throw exceptions. And so a simplification of it looks like this, where we have input values coming in here, they come into our function right here, and then you have some kind of output here. And the key is that there's no side doors, there's nothing for anything to come in here. We're not reaching out anywhere else into the world to try to mutate anything, and we're not mutating these things either. We're not coming back out in this side and saying, you know what, I'm going to change all of these. So while of course this is a simplification, it gives you an idea of what a pure function is. So a pure function looks like an add function. Parameters come in the front door right here, there's a return value, and then the algorithm only depends on these parameters that came through the front door. Conversely, an impure function is something like this, where we attempt to convert a string to an int, but guess what? toInt will throw an exception. So if the string has the value hi mom, this is going to throw a number format exception and blow up your code. So we don't do that. We don't throw exceptions. We don't write impure functions. Instead, when it comes to errors, what we do is we use this thing called functional error handling. And in Scala, there are at least 3 ways to implement functional error handling. One is with the option type, which you see right here. This is the long version of this function. I can write this much shorter, but you can see what I try to do is I trim the string, then try to convert that into an integer. I try to do that right there. If it succeeds, I'll return a sum that contains the integer, and if that fails, I catch the exception right here and I return a none. Now both sum and none are subtypes of option, so that's a quick look at how that works. But a real key here is we're not throwing exceptions out of here to short circuit our code. We just return a value right here, and that value is an option type. A second data type we can use in Scala is called try. And I say that I want to try to do the following. So I want to try to convert that string to an int. But if this fails, the way try works is it has two subtypes. So if it succeeds, it'll return a successive int. And if this code fails, it returns a failure. But again, no exceptions to short circuit the code. We just return a value here. And a third type we use in Scala is called either, and you see its signature right here. And the way this works is I try to convert this to an int, I wrap that with this either function right here, and the way that works is if it succeeds, it returns the integer parameter in the right value here. If it fails, it returns a throwable value as the left parameter here. And a nice thing about either that I don't show here is that I can return any type over here I want. I can control this a little more over here, and then I can return a string or a custom error type right here. But a key is that this is the third error type we can use in Scala. And again, a real big thing is that we're returning values here. We're not throwing exceptions to short circuit the code. And now that we're talking about functional error handling, what we can do is look at the ZIO type for the first time. So the way ZIO works is it looks a lot like either, except it has one more parameter. And we'll talk about this later. So the way this works in ZIO is that I attempt to convert that string to an int like I usually do right there. Then if it fails, I catch the exception and I transform that into a failure message. So here I'm saying I want to fail and I want to create a string as the error type. So this is the error type right there, that's a string. So if this succeeds right here, there will be an int in this field. If this fails, then it will have this custom string right here in this field. So this parameter and this parameter right here, if you think about it, they look an awful lot like that either, because either has a failure value here and a success value here, and ZIO does the same thing. The failure value is here, success value is here. So this is our first peek at the ZIO type. So if we look at a summary up to right now, we could say that functional programming is about immutable values, immutable data structures, pure functions, functional error handling. It's also about functional data modeling, but we don't need that for this presentation. But what we have shown so far is pure functions, and that leads up to this question, well, what are we going to do about impure functions in functional programming? And the way that this works in ZIO and most functional programming systems is that we use effects. And now a slight simplification is to say that an effect is anything that a function does other than returning a value. And this is a key point. We want our functions to look like this. We want them to be like algebra. But in the real world, they can't always look like that because we have networks, we have databases, errors, dependencies, concurrency, logging, and so on. So we handle these other functions with the ZIO type like this and ZIO constructs like you see here and here. And when we do this, we say that we're creating effects using the ZIO type. And as I mentioned before, if you used either before for error handling, ZIO is just one step beyond that. So you saw the ZIO type signature, and I didn't explain that first parameter before, but now I can. This first parameter we call the R parameter. It's the environment type. This value here can contain your dependencies. And then I already showed the other types, E and A. E is the error type and the error value right there, and A is the success type and will contain the success value. So as you saw with the string to int function, it didn't have any environment requirements. So we said that any old environment will work right there. And then the error type was a string and the success type was an int. And with ZIO, really one of the hardest things really is just the type signature here can be a little long and difficult to read if you're not used to that. But what we can do with ZIO is use Scala type aliases to simplify that ZIO type. So it turns out that there are patterns like this one, and this one that are actually really common. So we can use shorter type aliases like this one instead of this longer one over here. And the same for this and this. So as just one example, we say that UIO is an unexceptional IO, and we specify the success type right here. So the way this works is we say any old environment will work. We're not going to have any errors right here. So the only important parameter really is the int. So instead of writing this all the time, we just have to write unexceptional IO with that int, the success value right here. And task is similar to UIO. The only difference here is it can fail with a throwable, but because this pattern is so common, again, we just call this one a task of int, and we just specify the success value. And the third type alias is here, and again, the only difference with that one is we can have a custom error in this field. So there we call that with IO, we specify the custom error, and we specify the success type. And I mentioned earlier that ZIO is a little like the Scala either type, and you can see that over here. With either, you have the success type here and the error type here. We do the same thing with ZIO. You have the success type here, the error type here, and again, the difference here is you can also specify an environment that your code requires as the first parameter. And the reason I mention that is because our conceptual model of ZIO looks like this. So if you have a ZIO type and the first parameter is connection, the second one is string, third is int, you could think of that as being a function that takes a connection type as its input parameter, and then it transforms that into an either value of a string and an int. So if you're ever struggling with the ZIO type like this, just remember this conceptual model. It's like you're getting a connection into a function, and then you're transforming that into an either result like that. And now at this point, a great question might still be, why should I use effects? And an enormous key about this is because effects compose. You can do anything with effects that you want over here. This is a real simple example where I say this will always succeed with 40, this will always succeed with 2. So the result is going to be 40 plus 2, and that's going to be our sum over here. But you can have any kind of effects over here, and you can get them to compose. And that leads to a great question. What in the world is composition? Anytime we use the word composable, what we're saying is that we can combine small, proven parts to create a larger, rock-solid system. And I can't overstate how important composition is to functional programming. We create a bunch of functions like this, either as pure functions in some cases, or as effects in these cases, and then we combine them one after the other, like this right here, to create a solution. And a really important thing about composition is that we don't have exceptions flying out of these functions to ruin our code. Basically what we do is we program on the happy path, and then the unhappy path takes care of itself. So if we come back here, you see that maybe sum is going to be my value coming out of the composition of these three effects right here. So now what I mean by the happy path is that you just work with maybe sum like it succeeded. So you say, okay, well now what I want to do is I want to map that, and I want to create that variable here. And then once you have this one, you say, well, maybe I want to map that again to create some other final number. And all I'm trying to indicate is that you keep working with code like this and code like this, and you may have dozens and dozens of lines, and the entire time you just worry about the happy path or the success path. Because the way it works out is if you ever have a failure in there, when you get to the end of the code, when you have this final number right here, you can handle both the error value and the success value right here. So you can use a function like fold ZIO and say, if I had an error anywhere in all of this code, now I want to handle that value. And in this case, I'm just printing the error. But that's what I mean by happy path, is you just program here like everything is working. And then only at the end do you have to worry about the error. And then, of course, if everything succeeds, you work with the value that you wanted to work with. And now getting back to composition, a really cool thing is that you can compose concurrent code. So in this case, I just add some arbitrary parallelism. I say I want to fork this to create a new fiber. I want to fork that to create a new fiber. And then I zip those two fibers together so that when they're done, I get a result out of here. But this is enormous because I can do anything I want over here that includes pure functions, effects, parallelism, and I can compose all of those together just like that and get a result. And that's what my code looks like. And in fact, ZIO effects compose when you need to use error handling, concurrency, resource management, asynchronous I/O, scheduling and retrying, stream processing, dependencies, and more. All of these things that are so difficult simply compose in ZIO. And speaking of more, how about more composition? So this is a ZIO application. I can tell because it has extend ZIO app default. So this is the name of my application. I have a function here. It's called getName. It takes in a prompt. And then inside of here, I call readLine with that prompt. So what that does is I prompt a user for something and then I read their input. And this returns that ZIO type right here. So this effect can work with any environment, does not throw an error, and returns a string when it succeeds. Then I have another function here called greetPerson. It takes in a name, and then I print the name. Then I have a delay of 1 second, just to show you another thing that ZIO can do. And because this one just prints output, the success type over here is unit. Now my complete program looks like this. I print a line and I say hello. Then I call getName right here, and then I greet the person right here. And this is my full application right here, these 3 lines. So that's a program. And the way you work with ZIO, when you're using ZIO app default, is you define a run function or value right here. And whatever is over here is your application. So this is my program. And then in this example, I just say that, okay, run is equal to program. And remember again, the ZIO types are maybe one of the harder things to read. And we can simplify all of these. I just didn't bother to do that here. So I can show you more and more composition. This is another ZIO application. That's the name of it. These functions are the same or similar to the previous ones. And then all I do down here in my program is now I have more and more composition down here. So I have a print line. I call get name 3 times, print line there. And then I throw in a little bit of parallelism here just to make things interesting like that. And the only thing I'm trying to show in here is that all of these things compose with the error handling and even with parallelism. Here's another ZIO application. I call this one temperature converter. A few keys about this one. The first one here is that this is a pure function right here when I convert Fahrenheit to Celsius. A key about functional programming is you want to write pure functions as much as you can. So when you can, you write a pure function, and when you can't, you write effects like this one, and this one. Now, most of these effects are the same, but I do a little something different here. And what I say here is when I try to convert that to double, what I do want to do is return a number format exception as the error value right here. So this is one way you do that in ZIO. Other than that, the code is very similar to what you saw before. Now you see the error value here in my program is number format exception, but everything composes just like we want it to, including this pure function call right here. Then another difference down here is when I run my program, what I do is I catch all the possible errors coming out of that program, and then I print them with this message right here. So this part right here starts to show more of what we can do in the run value. And notice what we used in this code. We used immutable values, immutable data structures, pure functions. We used different types of effects, including error handling and concurrency, and they all composed. What's that? You want more? How about rock-solid resource management? With ZIO, we can open a resource like this in the first parameter group. In the second parameter group, we say this is how to make sure that resource is closed. And then where this comment is, you just use your resource inside of here. And that resource can be anything you want, like files and databases, connection pools, network access, etc. ZIO has all kinds of concurrency functions built in, so you can do things like run all of these in parallel and then collect them when you're done. You can race to effects, so you say run this one, and whoever finishes first is the winner right over here. And I already showed fiber management a little bit earlier. ZIO has all kinds of functions that we can use to work with error handling. We have catch all, catch some, or else, and then all of these down here are other functions that we can use for error handling. ZIO also has a streams package you can use. The ZIO test library also lets you test these effects. So you can create effects and then you can test them like this. So this one is a simple example, something that will always succeed. But the assert ZIO function lets us confirm that this result is equal to this result right here. And ZIO test has all kinds of built-in functions like this to make it really easy to test effects. Now I'm going to throw one more application at you here real quick. So what this one does is it creates an HTTP client. And then what I'm going to say is I want to go to this URL and get a response from that. Then I want to get the JSON body from that as a string. And then in here I want to try to convert that to JSON. I know it can fail, so I use from either right there. But if it succeeds, I'll have this data type right here. So this is my program up here. One thing I want to note too is when we talk about algebra, sometimes you can think of this as being an equation. So this is like an algebraic equation over here. So whether you like equation or you like program, either one is just fine. Now we come down to the run value here, and what's new here is that I am providing dependencies to this application. So for this application up here to work, I need to provide that client that we use right here. I also need to provide this thing called a scope. But this is how we provide dependencies to a program like that. And then when the program is finished running, I use fold ZIO like I showed before to handle the failure and success values just like that. And checking for failures is important because, of course, we want this code up here to succeed, but it can also fail. And ZIO makes it really easy for us to deal with failure and success. Okay, that was a lot to cover, so let's give it a quick recap. ZIO is a functional programming library. Functional programming deals with immutable values, immutable data structures, pure functions, functional data modeling, which I did not cover, and when we can't write pure functions, we use effects. As a pop quiz, do you remember what an effect is? A simplification is to say that an effect is anything a function does other than returning a value. And in ZIO, we create effects with the ZIO type. And I mentioned that ZIO is like either. And conceptually, we can think of that ZIO type here as a function that takes this environment parameter and returns an either, like that. And then an enormous part about functional programming is composition. We can compose all kinds of things like errors, concurrency, resource management, retries, scheduling, and all the other things I showed before. But the key in ZIO is that whatever you're doing, they all compose. One more thing about effects is that a lot of people say they're like blueprints, but to understand that, you're going to have to watch my other videos. I'm not going to get into that here. Then the final thing I want to mention is how is ZIO different than other functional programming systems? I'll summarize it like this. and say that ZIO is pure functional programming. There are no side effects allowed. Compared to other FP systems, ZIO is unique in how it handles concurrency and parallelism. As you saw in some of the examples, ZIO simplifies managing complex asynchronous workflows with guarantees about error handling, resource cleanup, and interruption. ZIO is also unique in that the error type forces us to handle or propagate errors explicitly. This gives us compile time safety and also makes it easy to reason about what can fail. And compared to other functional programming systems, ZIO is more type-safe. All of our effects are encapsulated in a strongly typed way. That's all great, but what's a huge difference about ZIO? The way I like to explain it is that ZIO is functional programming simplified. If you noticed in all of our code, there was no category theory. And that's crazy, right? Because when people talk about functional programming, they're always using terms like monad and monoid, functor and semigroup and so on. But the worst thing I showed in any code is that we have this ZIO type that we have to work with. And again, we can simplify that in many situations. So you don't need to learn category theory to use ZIO. You can learn it if you want to, but you don't need to. And that's why I say ZIO is functional programming simplified. And I'd like to think I know a little bit about this topic because I just happened to write a book with the same name. If you made it this far, congratulations. You've come a long way in a short time. At this point, I'd like to add 2 more notes here. First, my videos don't always go this fast. For this particular video, I just wanted to cover a lot of ground as fast as possible. And if you feel like you hung in there and you have any idea at all about what I talked about, I think you'll do just fine learning ZIO. Second, a big reason we say that a ZIO effect is like a blueprint is because the ZIO website and the official ZIO book describe a ZIO value as a blueprint for a concurrent workflow. To show what I mean, let me paste this code in right here. So if you're familiar with procedural code, this is the kind of code we write. We say that we have a value or a variable here. I call it go shopping unsafe. And we say it's equal to the Scala println function with the string right here. So then let me hit enter. And the key about this is that it does exactly what that says right there. It prints go shopping right away. But something I never thought about until I learned functional programming is what's going on here is we're describing both the what, as in what I want, and the when. And the when is actually right now in procedural programming. You saw that was printed right away. Now we can modify this code by wrapping it in a ZIO. And I will say ZIO.attempt. So I'm wrapping that print line there, and then I'm going to change this variable name to just go shopping. And you saw this output here. So now a good question is when I hit enter here, what do you think is going to happen right down here? And you see in the result here, we have go shopping is the variable name, and then this is the type of that variable. And then everything over here defines a ZIO effect, and that effect is this blueprint. So up here you saw that go shopping output right away. Down here there's no go shopping output at all. What happens when you create a ZIO effect like this with attempt is that you're literally creating a blueprint or creating a data structure. That data structure is created right now. Nothing happens right now other than the creation of this data structure. This print line code is not run right now. It's waiting to be run later. So in this procedural code up here, we had the mix-up or the combination of what I want and when I want it, and that happened to be right now. When we program with effects, we define what we want, but the when is not right now. The when happens later, when I'm ready for it to happen. So we say a few things about this. One is that ZIO is a functional effect type, or an effect, as I mentioned earlier. An effect is purely a descriptive value. It's purely this data structure that we have created. Effects are values, so you can see that go shopping is our variable name, and then everything over here highlighted in blue is the value. And another interesting thing is not only have we separated the what from the when, we've also separated it from the how, because now that I have a go shopping value, I can add to that later. And for example, this is something you can't do with a Scala future. When you define a Scala future, it just starts running automatically. When I created go shopping here, nothing has happened yet. So now I can say, you know what, I want to go shopping, but not now. How about if we delay that for 1 hour? And now I have a new effect, and I should have given that a name. So if I come back over here, I can say go shopping in 1 hour. That'll be our new effect name. And now you see that's our new variable name. This is the ZIO type that describes that variable name. And this data structure over here is the value. And again, a huge key is nothing has happened yet. And you can tell because we haven't put in any output yet. Now, if I scroll back here, in the case of go shopping, let me copy that, because that will attempt to go shopping. What I can do in the REPL, and this is just something you can do in the REPL, is just say, I want to go ahead and run that right now. And the way you do that is with this unsafe run method. And again, this is just in the REPL. So I hit enter there. And now we see that go shopping has run, but it only ran when I was ready to run it. And some real power happens in functional programming when we separate this what from this when. So again, I controlled when I wanted to call this, and you do the same thing in your ZIO programs. And because I separated the what from the when right there, I'm able to use this variable and make other changes to it as much as I want, such as creating this variable to say run that in 1 hour. So there's much more to talk about here, and I just wanted to be able to hint at this a little bit more in this video. But a key is that when you are creating a ZIO effect, you really are just creating a blueprint. And again, we're separating this what from this when. So this time I really am done. My name is Alvin Alexander, and I want to thank you for watching.